In this video, I will show you the derivation of the equations of constant acceleration. All of these derivations come from the velocity versus time graphs. We already know that we can use the slope of the velocity versus time graph to get the acceleration, and the area under the velocity versus time graph to get the displacement. So we're going to use those two principles to derive two of the three equations, and then we're going to combine the first two into a third equation. First, let's define some variables. We're going to call the initial velocity of the object v0 or v0, and the final velocity simply v. And we're going to call the time interval over which this object is moving delta t, and this is the time axis. So v is the final velocity, v0 or v0 is the initial velocity, delta t is the time interval, and we will use the letter A for the acceleration of the object. And in this case, remember, the acceleration is the slope of the velocity versus time graph, and the slope is the change in the vertical axis over the change in the horizontal axis. So delta v over delta t. And delta v is the final value minus the initial value. So v final minus v initial divided by delta t. So we have A equals v final minus v initial over delta t. I can rearrange that by multiplying both sides by delta t, and I get acceleration times time, A delta t, is final velocity minus initial velocity. And then I can rearrange that again by adding v0 to both sides, and I end up with final velocity is initial velocity plus acceleration times change in time. That is the first of the three equations of constant acceleration motion. The second equation is derived using the area under the graph. And so again, this is the initial velocity, this is the final velocity, and this is the time interval delta t over which the motion is taking place. And so we use the letter D for displacement, and displacement is final position x minus initial position x0. So we're going to find the area under this graph by finding the area underneath in this rectangle here, and then the area of the triangle. So the displacement, which is the area, is the rectangle plus the triangle on top. And the rectangle, the area is the base times the height. The base is delta t, and the height is the initial velocity, this height right here. That's the initial velocity. So that area is v0, the height, times the base, delta t. Plus the area of the triangle, which is 1/2 of the base, times the height of that triangle, which is v minus v0. So that is the displacement. That is x minus x initial. And we are going to simplify this a little bit because we know from our previous slide that this expression is A delta t. So v minus v0, from the definition of the slope of the velocity graph and from the definition of acceleration, v minus v0 is A delta t. So if I substitute that in, I get v0 delta t plus 1/2 delta t times A delta t. So here I have delta t times delta t, which is delta t squared. So my expression becomes x minus x0 is v0 delta t plus 1/2 A delta t squared. This is more commonly found in your textbook as x equals x0 plus v0 delta t plus 1/2 a delta t squared. So that is the second equation of constant acceleration motion. It's probably the first equation on your AP Physics 1 equation sheet. Either that or equation 1 is, I'm not sure. I'm not looking at it right now. The third equation comes from combining the definition of acceleration and the definition of average velocity. The definition of average velocity, v average, is equal to the displacement x minus x0 over t. So x minus x0 equals v average times t. And for constant acceleration, because the velocity graph is a straight line, in this very special case, the average velocity can be found by taking the initial velocity plus the final velocity and dividing by 2, only under conditions of constant acceleration. So now I have x minus x0 equals v average, which is v initial plus v0 over 2 times time. Now, from my first equation, I know that v equals v0 plus at, and if I rearrange that a little, v minus v0 equals a times t. So t can be written as the change in velocity, v minus v0, divided by the acceleration. If I substitute this in, I can eliminate t from my equation and have an equation that I can use that no longer has time in it. So x minus x0 equals the quantity v plus v0, remember, over 2. Remember, that's our average velocity, and time is v minus v0 over a. So if I put that over a common denominator, what you see in the first part, in the numerator rather, what you see in the numerator is the difference of squares. V plus v0 times v minus v0 is actually v squared minus v initial squared. And there's a 2 in the denominator and an a in the denominator. And that is equal to the displacement x minus x0. Now I'm going to multiply both sides by 2a. So 2a times x minus x naught is equal to v squared minus v0 squared. So sometimes you will see this equation written as v squared minus v0 squared is 2a delta x, where delta x is the displacement, x minus x0. So that is our third equation of constant acceleration motion.